Alright, here's another interesting exercise, and one where you do need to be a little bit careful, because this condition is you're concerned with G being invertible in M, but G inverse G2, G1 inverse G2 being in G. So, anyways, so it's an if and only if, and so we got to prove each direction. So to prove this is trivial because everything basically follows by the definition of a subgroup. If you have any element in your subgroup, then it's invertible in the subgroup, and in particular it's invertible in M because G is a subset of M. And obviously if G1 and G2 are in G, then G1 inverse is in G, and so and by closure under multiplication, G1 inverse times G2 is in G. And so everything that you need to know follows from the definition of a subgroup. So the other direction is the one that is a little more interesting. Let's see here. So for the reverse direction, let's see here, in my notes I wrote out all the stuff, which is unnecessary. Since G is non-vacuous, there is some G in G. Let's see here, then, let's see here, so G is invertible, so G is invertible in M, and G inverse G, which is 1. Well, 1 is just G inverse G, but this is in G by this second condition here. And so 1 belongs to G, and so that's good. Then, for all G in G, we want to prove that this is a subgroup, so we want to prove closure under inverses, and so, let's see here, so what is G inverse? Well, G inverse is just G inverse times 1, and because G is in G, G inverse is in M, and 1 is in G, and so this product here is in G. So there's that. Lastly, if H and G, or G and H are in G, then since G inverse is in G, which, so this actually, it matters what order you prove these things in, because we actually needed to do it in this order, at least for this proof. This proof that I'm doing would not have worked if you flipped the orders, because you needed 1 to be in G in order to get that G inverse was in G. And you need G inverse to be in G to do what we're about to do. So, since G inverse is in G, we want GH to be in G. Well, this is just G inverse H, which is in G. Because G inverse is in G, and so that's just this condition, but with G1 replaced by G inverse, so it's G inverse inverse. Okay. And that's it. We're done. That shows that's everything you need for a subgroup, because associativity is inherited from the fact that this is a monoid, so all you need for it to be a group are the closure properties, and it satisfies everything, so we're done.